This is a presentation which was held in Singapore in December 2019 during the SINCE conference, NDT conference in Singapore. And it is dealing with one of a particular feature available now in some of the latest instruments in the market, which is called CAD file importation. This feature improves and simplifies the evaluation of inspection results, especially for complex geometries for phased array inspection. But before I go deeper into that, I just want to highlight some of the special features related to phased array technology, what are the benefits and so on. Of course, phased array technology increases safety and product quality. Why? It's just simple to answer, because we have a much better volume coverage during inspection, which leads to higher probability in flaw detection. Better volume coverage because we not only inspect with one particular angle, we use a range of angles. For example, let's say 37 degree up to 75 degree in 1 degree steps, and that leads to a better volume coverage. Another thing which is quite important, I feel it's one of the most important features developed in the last years in phased array inspection, is the advanced coupling control technique. With this technique, we not only check a range of angles, which are electronically produced, every single angle in certain steps, we also check for the backwall echo. That means we send down perpendicular one particular beam to see or to check whether the backwall echo is present. If the backwall echo is present, it means we have a good coupling. If the backwall echo is not present, or it is of low amplitude, means below a certain threshold, then of course we have a bad coupling, not sufficient coupling, let's say. And that is monitored by the system while we do the scanning, so that the operator knows when the coupling is not good enough. And it's also recorded. All those information is also recorded. The coupling quality is recorded. This is a great advantage of phased array technology over conventional technology, because conventional technology always had this weak point that you fully depend on the operator. If the operator doesn't do a good job, maybe doesn't look for good coupling all the time, not applying enough coupling whatsoever, he will miss some data. And that is of course dangerous, because missing data means potentially missing flaws. And there was never a way of get some control about that. You depend 100% on the operator. Now with this phased array technology and the advanced coupling control technique, that's over. You now have complete coverage and complete information about the coupling quality during the whole process of inspection. One more advantage came with the combined PA and TOFT inspection method, which is somehow called do-it system, which actually means you have two phased array probes besides the weld, from the left side of the weld, from the right side from the weld. You check simultaneously from both sides of the weld, and at the same time you can also use TOFT probes, all in one particular scanner. TOFT probes, one set or two sets of TOFT probes two sets for higher thickness, and that means in one scan you get all data for phased array, both sides, and TOFT as well. So this is also a very economical method, because you also do full raw data storage. All the raw data from both sides of phased array and TOFT data will be stored. And it's always also related to the position of the scanner. That means it's an encoded scan. For every single position we have all those data. That increases definitely a lot of in safety and product quality. Yeah, and finally there were more and more improvements made over the years to get a better chance for data analysis and evaluation. Some manufacturers, or one in particular, one manufacturer displays the geometry on the screen, the complete geometry of a particular part. Of course, you need special software for that, dedicated for that particular weld, for example. So it's an economical issue here, because it's quite expensive in some cases. And now the new feature is the CAD importation. That means you can just take a drawing of the particular weld you are going to inspect, have that drawing made as a cut file, CAD file, and import it into the instrument. And then you can do the proper evaluation easily. You will see it later on. But before I go to that, a bit of more basics, let's say, for phased array technology. Why is it so not only important? How can we make sure that it's code compliant when we do phased array technology, when we use that technology? Yeah, first of all, what we need to do is we need to apply the DAC function or TCG function. DAC is distance amplitude correction. TCG is time corrected gain. I will explain what that means for those people who are not so familiar with it. We see here on that picture on the left, we see a phased array probe placed on a calibration block. We have here a number of side drill holes, which are now used to do some kind of calibration. What we do is, for example, we try to get a response from the first from this side drill hole, and you see we are beaming in that direction. We optimize the amplitude. This is similar, or it's actually the same as for conventional technology. You do the same with the DAC function, and you get an amplitude on the screen on that size, rather high amplitude, and then you move forward to the next one, the next one, and on the right you see now we are taking the response, the reflection from one of the side drill holes, which are in a further depth or further away from the probe. Also here, after optimization of the amplitude, we get some maximum amplitude, and you will see that it's much lower. First of all, it comes later because it's a longer way to reach that reflector, and then the amplitude is much smaller. Since the amplitude is much smaller, we have a drop of amplitudes over the length of the distance. And that function related to this drop of amplitude, which is actually a loss of sound energy on the way, this has to be considered when we want to do a code compliant inspection. We need to compensate for that loss of energy. And that can be easily done when we apply a DAC function. This is a DAC function. It's one example how a DAC function may look like. So suppose you have an amplitude over here, and you see that amplitude touching the curve, yeah. And now we check for the same size of flaw, like a side drill hole in a further depths. We get that type of amplitude, this height. So that means along the way, the farther the distance is of the side drill hole of the artificial flaw, the lower the amplitude, and that curve reflects that function. Now once we have that curve, we can now activate a TCG function. What does the TCG function do? It just puts everything on the same level. That means an amplitude which came here, let's say, remains on that level. If an amplitude comes here, it will be increased to that level. We put more gain on that amplitude. And this is going on for all the amplitudes which might come and touch this gate, this curve, will all be set on the same level. So if we find a flaw in different depths, different distance, a flaw of the same size, and we put everything on the same amplitude, then we have a code compliant inspection. Let's say the first part of it, it's code compliant in respect to the loss of energy. It's the same as for conventional technology, nothing special for that. What is special is some other function, what we call the angle gain compensation. And in order to understand what that means, this is particularly special for phased array technology. We have to see and understand the difference in doing the inspection for conventional and for phased array. Conventional technology means we are applying one angle only, and we have a probe with one angle, and we move that probe forward to the weld and then go back, forward and back, and we do that in a so-called zigzag mode. This is the way how conventional inspection works. To make sure that we cover a good volume, we have to move forward and backwards. But this is all covered with one particular angle only. Now coming to phased array here on the right. On the right you see there is a phased array probe, and we just move that in parallel to the weld. So it remains always in the same distance to the weld. Why can we do that? Because we are covering a range of angles. We don't need to move forward and backward. We're covering a range of angles. But one thing has to be considered. Depending on the angle itself, we have sometimes a longer way for the sound to travel, and sometimes a shorter way for the sound to travel. Yeah? I think this will become more clearer in the next picture. Here we have this function we call angle gain compensation. Let's look at this 0 line here. 0 dB means this is one particular amplitude height. Let's put it on 80% screen height. Response from one particular side drill hole, maybe 3 millimeter whatsoever. We get the amplitude height of 80%. Now we get that when we work with 45 degrees. So we just consider a phased array angle of 45 degrees. But we are covering a whole range of angles from, let's say, 37 up to maybe 72 or something like that. So what happens when we look at a higher angle? When we look at a higher angle, like 59 degree, we will find that the amplitude is lower. It is lower because the sound travels a longer distance to the wedge, through the wedge, for example. Some other factors also are important here to consider. But the effect is that the amplitude is lower. So that means we need to increase the amplitude to reach the same level as with 45 degree. Yeah, when we look at 59 degree here, we might need to add about 3 dB. That means the instrument must automatically add a particular amount of gain in order to make sure that all reflections from one particular flaw, same size, comes with the same amplitude. Only then it's code compliant. All right. So finally, when we apply the DAC function and the angle gain compensation function, it leads to a fully code compliant inspection. And here is an example for that. We have a calibration block here with a number of artificial floor side drill holes. We have the probe placed on top, and now we see the response from those flaws in one sector scan, so-called sector scan. This is the range of angles we are covering, from the lowest angle to the highest angle. And the probe sits just and is not moved at all. It sits on top of this block, and on this sector scan, in the sector scan we see all those indications representing the reflections from those side drill holes. And they are coming all in the same color. That means they are of the same amplitude. So it's fully code compliant. All reflections from the side drill holes are shown with the same intensity here, the same amplitude height, independent from the distance and independent from the incidence angle. That's fully code compliant. So I hope you have now a better understanding about the general things to be considered when you work with phased array. So now we touch something else, the challenges in evaluating phased array scan results. First of all, we take a look at this picture on the right, where we see there's a phased array probe. We see the sector scan in green color here. We see the bottom here, the end of the test body, test specimen. We see that there is a side drill hole, and we see the number 1 and number 2. What does that mean? That means under one particular angle we get a response from a reflection from the side drill hole directly. This is number 1. But also under a smaller angle we get some feedback from that side drill hole, because this beam goes back to the back wall, then goes up and hits the side drill hole from this position. So this is number 2. So we get 2 times an indication from one particular flaw. And here on the left you see the sector scan with 2 indications, 1 and 2. So means you have one flaw, but you get 2 indications in this case. It's rather simple to understand because it's a very simple geometry and nothing special with that. So I think everybody can easily understand that and work with it. What happens when you have a complex geometry like this one? That's a real challenge, because here on the left you see there is a block to be inspected which has a different contour altogether, and it would be hard to make a special software for that one. It's possible, yes, but to make that will probably cost a lot of money. Maybe not worth to do it. But anyway, there's another opportunity to do this inspection now. Not only to do this inspection, to do the evaluation. What we get here from this setup is here on the right, we see a sector scan. The sector scan shows us the number of indications, 1, 2, 3, 4, 5. So we don't know where they are coming from. So that's not so easy to evaluate by operator. We get some reflection from the geometry, but also might be flaw indication, we don't know. And now the new feature available in some instruments, allows us to import the CAD file. And when we import the CAD file and we put it on top of the sector scan, which is done over here, you now see where the indications are coming from. For example, this indication here on the top right in the sector scan, this one comes from the geometry, the one below also from the geometry, the one on the left from the geometry, but this one in the center here is a flaw indication. So now for the operator, for the person who does the evaluation at the end, it is rather simple to make the analysis once he has used the imported CAD file. Alright, if you have questions to this presentation, just do not hesitate to contact us on the info@united-ndt.com. Thank you very much.